Welcome back to Science Lullaby, where we explore the wonders of science in a way that helps you drift peacefully into sleep. Tonight, we're going to examine one of humanity's most profound questions, a question that has captivated minds for generations and continues to drive some of the most ambitious scientific projects ever undertaken. Do aliens exist? More specifically, what evidence do scientists actually take seriously when they consider this question? This isn't a journey into speculation or science fiction. Instead, we'll walk through the actual discoveries, the real missions, the tangible data that researchers around the world are carefully analyzing right now. We'll visit distant exoplanets where telescopes have detected intriguing chemical signatures. We'll examine rocks on Mars that might preserve traces of ancient microbial life. We'll listen in on the radio searches scanning billions of frequency channels. We'll explore icy moons with vast oceans hidden beneath their frozen surface. The story we're about to tell is one of patient observation, rigorous analysis, and profound implications. It's a story where every claim must be backed by evidence, where every exciting discovery comes with careful caveats, and where the absence of proof isn't the same as proof of absence. So, settle in, get comfortable, and let's begin this journey through the cosmos, examining the evidence that keeps scientists searching, hoping, and wondering about life beyond Earth. To understand why scientists take the possibility of alien life seriously, we first need to appreciate the sheer scale of the cosmic stage on which this drama might be playing out. When we look up at the night sky, we're seeing only the tiniest fraction of what's actually out. The stars visible to the naked eye number perhaps a few thousand on the clearest nights, but this represents an almost laughably small sample of the universe. Our own Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. Think about that number for a moment. 400 billion. If you counted one star per second, it would take you more than 12,000 years just to count the stars in our galaxy alone. And each of these stars is a sun, a furnace of nuclear fusion, many of them accompanied by families of planets orbiting in their gravitational embrace. In 2013, data from the Kepler Space Telescope led scientists to a remarkable conclusion. The Milky Way contains at least as many planets as it does stars. This means our galaxy hosts somewhere between 100 billion and 400 billion worlds. Some are gas giants like Jupiter, massive spheres of hydrogen and helium with no solid surface to speak of. Others are rocky planets more similar to Earth, worlds with solid ground, where you could theoretically stand and look up at an alien sky. But the story doesn't end with our galaxy. The observable universe contains an estimated 2 trillion galaxies. Each one is a vast city of stars, and if the same planet-to-star ratio holds throughout the cosmos, then the number of planets in the universe becomes almost incomprehensibly large. We're talking about numbers so vast that they lose meaning to the human mind. Trillions upon trillions of worlds scattered across the immense darkness of space. Within this vast cosmic population, scientists focus their attention on a specific subset, planets that might be capable of supporting life as we know it. This involves looking for worlds in what astronomers call the habitable zone, sometimes referred to as the Goldilocks zone. This is the region around a star where conditions are neither too hot nor too cold for liquid water to exist on a planet's surface. Why is liquid water so important? Because every form of life we've ever encountered on Earth requires water. It's the universal solvent, the medium in which the chemistry of life takes place. Water molecules have unique properties that make them essential for dissolving nutrients, facilitating chemical reactions and maintaining the structures of biological molecules. While it's theoretically possible that life could evolve using a different solvent, water is what we know, and so water is what we search for. The habitable zone isn't a fixed distance from every star. It varies depending on the star's size and temperature. A massive hot star has its habitable zone much farther out than a small cool red dwarf. For our Sun, the habitable zone extends roughly from the orbit of Venus out to the orbit of Mars, with Earth sitting comfortably in the middle. But being in the habitable zone doesn't guarantee that a planet will actually be habitable. Venus is technically in our Sun's habitable zone, yet its surface temperature exceeds 450 degrees Celsius due to a runaway greenhouse effect, hot enough to melt. Still, recent discoveries have shown that rocky planets in the habitable zones of their stars are surprisingly common. Astronomers estimate that roughly 1 in 5 Sun-like stars has an Earth-sized planet in its habitable zone. Given the hundreds of billions of stars in our galaxy, this suggests tens of billions of potentially habitable worlds in the Milky Way alone. The nearest of these might be within just 12 light-years of. As of late 2025, astronomers have confirmed the existence of more than 6,000 exoplanets, planets orbiting stars other than our Sun. This number has exploded in the past 3 decades. Before 1992, we had never confirmed a single planet beyond our solar system. Now we know of thousands, with thousands more candidates awaiting confirmation. The Kepler Space Telescope alone identified several thousand candidate planets during its mission, fundamentally transforming our understanding of how common planetary systems. These discoveries have shifted the question from "are there other planets?" to "which planets might host life, and how can we detect life if it exists there?" The search has become more focused, more sophisticated, more hopeful. We now know that the universe is rich with worlds, and the conditions necessary for life, at least as we understand it, are far more common than previous generations dared to imagine. This abundance doesn't prove that life exists elsewhere. The universe could be teeming with sterile worlds, planets with all the right ingredients, but no spark of life. Or it could be that life is common, but intelligent technological life is vanishingly rare. Or perhaps we're looking in the wrong places, searching for the wrong signs, unable to recognize alien life even if we encounter it. But the sheer number of opportunities, the vast multitude of worlds where life could potentially arise, gives scientists legitimate reason to take the search serious. In a universe this large with this many planets, it would be extraordinarily surprising if Earth were the only place where the chemistry of life ever got started. While astronomers search for potentially habitable worlds, another group of scientists has been listening. For more than 6 decades, researchers involved in SETI, the search for extraterrestrial intelligence, have been pointing radio telescopes at the sky, hoping to detect signals that could only come from technological civilizations beyond Earth. The modern era of SETI began in 1960 with a project called OSMA, led by astronomer Frank Drake, using an 85-foot radio telescope at the National Radio Astronomy Observatory in Green Bank, West Virginia. Drake monitored 2 nearby Sun-like stars, Epsilon Eridani and Tau Ceti, for 6 hours each day over several months. He slowly scanned frequencies near the 21-centimeter wavelength, a frequency that naturally occurring hydrogen gas emits, and one that alien astronomers might logically choose for interstellar communication. The project was modest by today's standards, inexpensive, and straightforward in its approach. It detected no alien signals, but it established a methodology that would guide SETI searches for generations to come. The fundamental principle behind SETI is elegantly simple. If an advanced technological civilization exists elsewhere in our galaxy, they might be broadcasting radio or optical signals into space, either intentionally to communicate with other civilizations, or inadvertently as electromagnetic leakage from their technology, much like Earth has been doing since the advent of radio and television. These signals would travel through space at the speed of light, and if we happen to be looking in the right direction at the right frequency at the right time, we might detect them. But the challenge is enormous. The radio spectrum is vast, extending from frequencies of 3 kHz up to 300 GHz. Within this range there are countless possible channels where a signal might appear. It's like tuning an old radio, trying to find a station, except instead of scanning through a few dozen stations on your dial, you're scanning through billions upon billions of possible frequency, and you have to point your antenna in exactly the right direction, toward the exact point in the sky where the signal is coming from. To make matters more complicated, Earth-based technology creates an enormous amount of radio interference. Cell phones, Wi-Fi routers, satellites, GPS systems, radar installations, and countless other human technologies all emit radio waves. Distinguishing a genuine alien signal from terrestrial interference is like trying to hear a whisper in a crowded stadium. SETI researchers have developed sophisticated techniques to filter out these earthly signals, but the challenge remains formidable. In 1999, a project called SETI at Home revolutionized the search by harnessing distributed computing power. Researchers at the University of California, Berkeley, created a screensaver program that millions of volunteers could download to their home computers. When the computers were idle, the screensaver would activate and analyze small chunks of radio telescope data, searching for patterns that might indicate artificial signals. At its peak, millions of people participated, contributing enormous computational power to the search. The project generated 12 billion detections, momentary blips of energy at particular frequencies coming from particular points in the sky. Over the course of a decade, scientists winnowed those 12 billion detections down to about 1 million candidate signals, then down further to 100 that merited closer examination. These 100 signals represent the most intriguing findings from 2 decades of SETI. Since July 2025, researchers have been using China's 500-meter aperture spherical telescope, the largest single-dish radio telescope in the world, to search for these signals again. If any of them are genuine alien transmissions, they should still be there, still broadcast. So far none has been confirmed, but the search continues. In 2015, a major new initiative called Breakthrough Listen, launched with $100 million in funding, committed to searching for intelligent extraterrestrial communications on an unprecedented scale. The project uses some of the world's most powerful telescopes, including the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, observing for thousands of hours every year. Previously, SETI projects might get 24 to 36 hours of telescope time annually. Breakthrough Listen operates at a completely different scale.
The project also employs cutting-edge technology. At Green Bank, dedicated hardware processes radio telescope data at a rate of 24 gigabytes per second, scanning billions of radio channels simultaneously. In 2025, researchers announced a revolutionary artificial intelligence system that operates 600 times faster than previous methods. This system can analyze signals in real time, searching not just for the narrowband signals that traditional SETI focuses on, but for burst-like or modulated transmissions that humans might not have imagined. An advanced civilization might use communication methods we haven't thought of, and this AI-powered approach can learn to recognize patterns that would escape human notice. Beyond radio searches, some SETI projects look for optical signals, flashes of laser light that an alien civilization might beam into space. These optical SETI programs use telescopes equipped with sensitive detectors capable of identifying extremely brief pulses of light that last only billionths of a second. A sufficiently advanced civilization could use powerful lasers to communicate across interstellar distances, and these signals would stand out dramatically from the steady glow of stars. Despite 6 decades of searching, despite millions of hours of observation, despite the analysis of enormous volumes of data, SETI researchers have yet to detect a confirmed signal from an extraterrestrial technological civilization. The Great Silence, as it's sometimes called, persists. The universe, as far as we can tell with our current instruments and methods, remains quiet. But this silence doesn't necessarily mean aliens don't exist. There are countless reasons why we might not have detected them yet. Perhaps they're too far away. Their signals too weak to reach us. Perhaps they use communication technologies we can't detect or don't recognize. Perhaps they existed millions of years ago or won't arise for millions of years in the future, and we're simply not synchronized in time. Perhaps intelligence is common, but technological civilizations are short-lived, burning bright for a few centuries before destroying themselves or transcending the need for electromagnetic communication. Or perhaps, as some researchers suggest, we simply haven't searched enough yet. The volume of space we've examined, the number of stars we've monitored, the range of frequencies we've scanned, all of this represents a minuscule fraction of the possibilities. One astronomer calculated that if the cosmic haystack of possible search space were the size of the Earth's oceans, we've so far examined about a hot tub's worth. We've barely begun. This is why organizations like the SETI Institute continue their work, why Breakthrough Listen pushes forward with ever more sensitive instruments, why researchers develop new techniques and approaches. The absence of evidence isn't evidence of absence. It's evidence that we need to keep looking, keep listening, keep refining our methods. The universe is vast, and the search has really only just begun. Every new observation, every improved technology, every innovative approach brings us closer to answering one of humanity's most profound questions. Are we alone? While SETI listens for technological signals, other scientists are searching for more fundamental signs of life, the chemical fingerprints that biological processes leave in a planet's atmosphere. This approach focuses on biosignatures, molecules or combinations of molecules that would be difficult to explain without the presence of light. One world has captured particular attention in recent years: K2-18b, an exoplanet located 124 light-years from Earth in the constellation Leo. Discovered in 2015, K2-18b is about 8.5 times as massive as Earth, and orbits a cool red dwarf star. What makes this planet remarkable is its location. It sits squarely in its star's habitable zone, where temperatures would allow liquid water to exist on the surface, assuming the planet has the right kind of atmosphere. K2-18b completes one orbit around its star every 33 days. Being so close to its star might seem to make it too hot for life. But remember, K2-18b's star is much smaller and cooler than our Sun. A red dwarf's habitable zone is much closer in than ours. The planet receives a similar amount of energy from its star as Earth does from the Sun, making its surface temperature potentially Earth-like. In 2019, the Hubble Space Telescope detected water vapor in K2-18b's atmosphere, the first time this had been confirmed for a habitable zone exoplanet. But the really exciting discoveries came in 2023 and beyond, when the James Webb Space Telescope, humanity's most powerful space observatory, turned its instruments toward this distant world. Webb detected methane and carbon dioxide in the atmosphere, carbon-based molecules that on Earth are intimately connected with life. Then came the potentially game-changing discovery. In both 2023 and subsequent observations, Webb detected what appear to be signs of dimethyl sulfide and dimethyl disulfide. These are sulfur-containing compounds that on Earth are produced almost exclusively by life. Specifically, microscopic marine algae called phytoplankton create dimethyl sulfide as part of their metabolism. These tiny organisms, floating in Earth's oceans, generate enough dimethyl sulfide that the gas plays a significant role in our planet's climate system. Finding these compounds on another world could be evidence of life. But scientists are exercising extreme caution. The signals for these sulfur compounds are weak, well below the threshold that researchers typically require before making extraordinary claims. Some experts have expressed skepticism, noting that K2-18b's atmosphere has produced false alarms before, with previous detections that turned out to be something else entirely. The presence of these molecules hasn't been definitively confirmed, and even if they are there, scientists would need to rule out non-biological explanation. K2-18b is what some researchers call a Hycean world, a hypothetical type of planet with a planet-wide ocean covered by a hydrogen-rich atmosphere. These worlds would be very different from Earth. The atmospheric pressure would be intense, the oceans potentially very deep, perhaps hundreds of kilometers deep. Life in such an environment, if it exists, would face challenges and opportunities completely unlike anything on Earth. Some researchers question whether Hycean planets can really remain habitable, noting that K2-18b might actually be too close to its star, too hot for liquid water despite being in the nominal habitable zone. Other exoplanets have also generated excitement. In November 2025, scientists announced the discovery of GJ25, a super-Earth less than 20 light-years from our solar system. This planet, almost 4 times Earth's mass, orbits in the habitable zone of its star, and appears to be rocky rather than gas. Its proximity makes it an excellent target for future observation. When the next generation of extremely large telescopes comes online, they'll be able to study GJ25-1c's atmosphere in detail, searching for biosignature. Similarly, HD 2079-4D, another super-Earth about 6 times Earth's mass and located just 20 light-years away, orbits in its star's habitable zone. These discoveries illustrate how common potentially habitable worlds may be in our cosmic neighborhood. The nearest potentially habitable exoplanet could be right next door on galactic scales. How do scientists detect molecules in the atmospheres of planets hundreds of trillions of kilometers away? The technique is called transmission spectroscopy, and it's remarkably elegant. When a planet passes in front of its star from our perspective, a tiny fraction of the star's light filters through the planet's atmosphere before reaching us. Different molecules in that atmosphere absorb light at specific wavelengths, creating a kind of chemical fingerprint. By spreading the light into a spectrum and looking for these absorption features, scientists can determine what gases are present. The James Webb Space Telescope excels at this work. Its enormous mirror and sophisticated instruments can detect incredibly subtle variations in starlight. But even Webb has limits. It takes hundreds of hours of observation to thoroughly analyze a single exoplanet's atmosphere, and each detection needs to be confirmed with multiple observations. Scientists must rule out false positives, instrumental artifacts, and alternative explanations before they can make confident claims about what they're seeing. This is why the language around exoplanet biosignatures is so carefully qualified. Researchers talk about potential biosignatures, possible signs of life, findings that could indicate biological processes. These aren't weasel words or lack of confidence. They're the appropriate scientific caution when dealing with data at the absolute limits of what our technology can detect. When making claims that would have profound implications for our understanding of life in the universe, the search continues to accelerate. More powerful telescopes are under development, including the Habitable Worlds Observatory, specifically designed to detect and characterize Earth-like planets around nearby stars. Ground-based observatories like the Extremely Large Telescope and the 30-meter telescope will have the resolution to directly image some exoplanets and analyze their atmospheres in unprecedented detail. Within the next few decades, we may have definitive answers about whether life exists on worlds beyond our solar system. But for now, planets like K218b represent tantalizing possibilities, hints and whispers that keep scientists searching. Each new observation adds another piece to the puzzle, another constraint on what these distant worlds might be like. The evidence isn't conclusive yet, but it's compelling enough to drive continued investigation, sophisticated enough to suggest that the question of alien life might be answered, not in some distant future, but within the lifetimes of people alive.
While we search distant star systems for signs of life, perhaps the most compelling evidence lies much closer to home. Mars, our planetary neighbor, has become the focus of intensive astrobiological investigation. The red planet's surface is cold, dry, and bombarded by radiation that would be lethal to most life as we know it. But Mars wasn't always like this. Billions of years ago, it was warmer, wetter, and might have been home to microbial life. NASA's Perseverance rover has been exploring Mars since landing in Jezero crater in February 2021. This robotic geologist, roughly the size of a car, carries an impressive suite of scientific instruments designed to search for signs of ancient life. In July 2024, while investigating an area called the Bright Angel Formation on the crater's western edge, Perseverance made what might be its most significant discovery yet. The rover encountered a distinctive rock that the science team nicknamed Shyava Falls, an arrowhead-shaped formation measuring about 1 meter by 60 centimeters. When Perseverance drilled into this rock and extracted a core sample, sealing it in a titanium tube, that sample became known as Sapphire Canyon. Over the following year, scientists analyzed data from multiple instruments, and what they found was intriguing enough to warrant publication in the journal Nature in September. The Bright Angel Formation consists of mudstone, ancient sedimentary rock made from clay and silt that settled out of water billions of years ago. On Earth, such environments are excellent at preserving evidence of past life. The mud protects organic materials and biological structures from degradation, allowing them to survive for eons. Finding similar rocks on Mars immediately suggested a promising place to search for biosignatures. Perseverance's instruments revealed that Shyava Falls contains organic carbon, the fundamental building block of life as we know it. It also contains sulfur, oxidized iron in the form of rust, and phosphorus. These elements combined in the right ways could provide energy for microbial metabolism. On Earth, countless microorganisms make their living by exploiting chemical gradients involving these exact elements. But what really caught scientists' attention were the rock's distinctive textures, features that earned them colorful nicknames. The leopard spots are small, irregular patterns visible across the rock's surface. The poppy seeds are tiny mineral grains distributed throughout. These aren't just pretty patterns, they represent specific minerals: vivianite, an iron phosphate mineral, and grigite, an iron sulfide mineral. On Earth, vivianite forms in sediments, peat bogs, and environments rich in decaying organic matter. Grigite is particularly interesting because some microbes on Earth can produce it as part of their metabolism. These organisms use sulfate as an energy source, and grigite is a byproduct of their biochemistry. The presence of these minerals in the arrangement seen in Chiava Falls could be explained by ancient microbial activity. Here's how the biological hypothesis would work. Imagine ancient Mars, 3.5 billion years ago. Water flows through what is now Jezero crater, depositing layers of mud and silt. Microorganisms, if they exist, colonize these sediments. They consume organic carbon and use chemical reactions involving iron, sulfur, and phosphorus to generate energy, much like certain microbes do in Earth's deep ocean sediments today. As they live and die, as their metabolic processes alter the chemistry around them, they leave behind distinctive mineral patterns. Over billions of years, the water disappears, the climate changes, the planet becomes the frozen desert we see today. But the rocks remember. The patterns persist, waiting for a rover to come along and recognize them. That's the biological hypothesis. But there's always the non-biological alternative, what scientists call abiotic processes. High temperatures can create similar mineral assemblages. Acidic water reacting with rock can produce complex patterns. Organic molecules can bind minerals together without life being involved. The challenge for scientists is determining which explanation better fits the observation. The research team emphasizes that they are not claiming to have found life on Mars. What they're claiming is that Sapphire Canyon contains what they call a potential biosignature. This term has a specific meaning in astrobiology. A potential biosignature is any substance or structure that might have a biological origin, but which could also have formed without life. It's a feature that warrants further investigation, that increases the probability that life was involved, but which doesn't definitively prove life's presence. The scientists note that while non-biological explanations are possible, they seem less likely given what the data shows. The rocks at Bright Angel don't appear to have experienced the high temperatures or acidic conditions that would most easily explain the mineral patterns through purely chemical processes. The combination of organic carbon, the specific minerals present, their arrangement, and the geological context all point toward biological activity as a reasonable hypothesis. But reasonable hypothesis is not the same as proof. This is where the cold scale comes in. The confidence of life detection scale is a framework that the scientific community uses to assess claims about potential life beyond Earth. It's marked by 7 benchmarks, each representing an increasing level of confidence that a particular observation genuinely indicates life. The Sapphire Canyon finding sits somewhere in the middle of this scale. It's compelling enough to warrant continued investigation, significant enough to publish in a major scientific journal, but not definitive enough to claim victory in the search for life on Mars. Importantly, Sapphire Canyon is just one of 27 rock core samples that Perseverance has collected since landing on Mars. These samples sit sealed in their titanium tubes, cached on the Martian surface. NASA and the European Space Agency are planning a Mars sample return mission, one of the most ambitious robotic endeavors ever attempted. If successful, this mission would retrieve the samples and bring them back to Earth, where laboratories around the world could analyze them with instruments far more sensitive and sophisticated than anything we can send to another planet. On Earth, scientists could perform detailed chemical analyses, examine the samples at the atomic level, search for specific organic molecules that would be hard to explain without biology. They could look for isotopic signatures, the ratios of different atomic versions of elements, which biological processes often alter in characteristic ways. They could search for preserved cellular structures, for mineral formations that could only arise through microbial activity. The samples that seem most promising on Mars, like Sapphire Canyon, would receive particularly intensive scrutiny. The story of Shayava Falls and Sapphire Canyon illustrates how the search for life on Mars has evolved. Early missions asked, was Mars ever wet? The answer was an unequivocal yes. Later missions asked, was Mars ever habitable? Again, yes. Vast regions of ancient Mars appear to have had all the conditions necessary for life: liquid water, energy sources, appropriate chemistry, stable environments lasting millions of years. Now we're asking the next question: did life actually arise on Mars? This is much harder to answer. Habitability doesn't guarantee habitation. Just because a place could support life doesn't mean life ever got started there. Origin of life is a complex, poorly understood process, and we have no idea how likely it is to occur even under favorable conditions. Earth might be one data point, or it might be an outlier, a cosmic fluke. But with every new discovery, with every carefully collected sample, with every sophisticated instrument deployed, we inch closer to an answer. Mars might hold the key to understanding whether life is common in the universe, or whether we're alone. The next few decades of Mars exploration will be crucial, and Perseverance's findings from the Bright Angel Formation might someday be remembered as the moment we found our first solid clues that life once existed beyond Earth.
While Mars holds clues to past life, 2 icy moons in our solar system might harbor life right now. In the present day, swimming through dark oceans hidden beneath frozen shells, Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, have become prime targets in the search for life, ocean worlds that might offer conditions for biology unlike anything we've imagined. Europa is slightly smaller than Earth's moon, a sphere of rock covered by a layer of water ice. But this isn't just a frozen ball. Beneath that ice lies a global ocean of liquid water, perhaps 100 kilometers deep. The ocean is kept liquid by tidal heating. As Europa orbits Jupiter, the giant planet's immense gravity stretches and flexes the moon, generating heat through friction in its interior, much like a repeatedly bent wire heats up. This process provides enough energy to maintain a vast ocean despite Europa being 5 times farther from the Sun than Earth. Enceladus is even smaller, only about 500 kilometers across, but it too has a global subsurface ocean. Saturn's gravity provides the tidal heating that keeps this ocean liquid. In 2005, the Cassini spacecraft discovered enormous plumes erupting from cracks near Enceladus's south pole. These plumes shoot water ice and vapor hundreds of kilometers into space, material that comes directly from the subsurface ocean. It's as if Enceladus is providing free samples of its ocean for us to study, and study them we have. When Cassini flew through these plumes, its instruments detected not just water, but also organic molecules, carbon-based compounds that are essential for life. They found methane, carbon dioxide, ammonia, and more complex organic molecules. In 2018, researchers announced that Cassini had detected macromolecular organic compounds, large complex molecules that on Earth are associated with biological processes. These weren't just simple carbon chains but elaborate structure. Even more intriguingly, the plumes contain molecular hydrogen. This is significant because hydrogen can serve as an energy source for life. On Earth, certain microorganisms called methanogens consume hydrogen and carbon dioxide, producing methane as a waste product. These organisms thrive in environments like deep-sea hydrothermal vents, places where hot fluids from Earth's interior mix with cold ocean water. Scientists suspect that similar hydrothermal vents might exist on the ocean floors of both Europa and Enceladus, places where minerals from the rocky core react with the ocean water, producing hydrogen and chemicals that could fuel metabolism. The chemistry detected in Enceladus's plumes is consistent with water-rock reactions occurring at temperatures suitable for life, reactions that mirror processes happening at Earth's deep-sea hydrothermal vents. These vents on Earth support entire ecosystems independent of sunlight. Bacteria use chemical energy to produce organic matter, and other organisms feed on the bacteria. It's a complete food chain powered not by photosynthesis, but by geochemistry. Could something similar exist in the oceans of Enceladus or Europa? The conditions seem right. There's liquid water, obviously essential. There's an energy source in the form of chemical reactions and tidal heating. There are organic molecules, the building blocks that life would need. There might be hydrothermal vents providing concentrated sources of chemical energy and nutrients. The oceans have existed for billions of years, providing ample time for life to arise and evolve. But there are challenges too. The oceans of these moons are probably alkaline, with pH levels higher than most terrestrial oceans. The pressure at the bottom of Europa's ocean would be intense, hundreds of times Earth's atmospheric pressure. The temperature, while above freezing, might still be quite cold by Earth standards, perhaps just a few degrees Celsius. There would be no sunlight, nothing but perpetual darkness. Any life that existed would need to be adapted to these extreme conditions. On Earth, we know that life can thrive in some remarkably harsh environments. Scientists have found bacteria in the scalding water of hot springs, in the crushing depths of the ocean trenches, in acidic mine drainage, in Antarctic ice, in solid rock kilometers below the surface. Life's tenacity and adaptability might extend to the alien environments of Europa and Enceladus. Recent research has added another encouraging sign. In 2024, scientists published work showing that amino acids, the building blocks of proteins, could survive on the surfaces of these icy moons despite harsh radiation from their host planets and from space. The radiation is intense enough to break down organic molecules, but the research suggests that biosignatures could persist in the ice, particularly if buried just a few centimeters below the surface. This means that future landers wouldn't need to drill through kilometers of ice to detect signs of life. They could sample the surface, especially on Enceladus, where fresh ocean material is continuously delivered by the plumes. Multiple space agencies are planning missions to these ocean worlds. NASA's Europa Clipper launched in 2024 and will arrive at Jupiter in the 2030s, making dozens of close flybys of Europa to study its ice shell, characterize its ocean, and search for suitable landing sites. The European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer, launched in 2023 and will study not just Europa, but also Ganymede and Callisto, two other Jovian moons that might have subsurface ocean. Concepts for an Enceladus orbiter have been proposed, missions that would fly through the moon's plumes repeatedly, analyzing their composition in exquisite detail. More ambitious ideas include landers and even cryobots, probes that would melt through the ice using heat, descending through the shell to reach the ocean below. These missions are technically challenging and decades away,
but they represent the future of ocean world exploration. The possibility of life in these hidden oceans raises profound questions. If life arose independently on Europa or Enceladus, it would prove that biology isn't unique to Earth. It would suggest that wherever conditions are suitable, life finds a way. It would mean the universe might be full of ocean worlds harboring their own forms of life, worlds we're only beginning to discover. But if we find no life on these moons despite conditions that seem favorable, that too would be significant. It would suggest that the origin of life is more difficult than we think, that the leap from chemistry to biology requires something rare or unlikely. It would make Earth's biosphere more precious, more remarkable, possibly more fragile. These icy moons, these ocean worlds, represent one of our best chances to answer the profound question of whether life exists beyond Earth. The evidence isn't there yet, but the potential is staggering. Every new discovery about these worlds, every mission that ventures out to study them, brings us closer to knowing whether we're alone, or whether life is a cosmic commonplace, hiding beneath ice in the darkness, waiting to be found. In recent years, another dimension has been added to the conversation about aliens: the official government investigation of unidentified anomalous phenomena, or UAPs, the term that has replaced the older designation of UFO. These investigations have generated significant public attention and congressional hearings. But what does the actual evidence show? The Pentagon's All-Domain Anomaly Resolution Office, known as AARO, was established in 2022 specifically to track and investigate reports of UAP. The office serves as a central clearinghouse for sightings and encounters, primarily from military personnel who observe things they cannot immediately explain. In its most recent annual report covering the period from May 2023 to June 2024, AARO received 757 new UAP reports. Of these, the office was able to resolve 49 cases during the reporting period. All 49 turned out to be prosaic objects: balloons, birds, drones, satellites, or conventional aircraft. Another 243 cases were recommended for closure as of June 2024, pending final review, and these also resolved to ordinary explanation. The vast majority of closed cases, about 70%, were identified as balloons, the kind of weather balloons or high-altitude research balloons that are launched routinely around the world. 16% were drones, 8% were birds, 4% were satellites, particularly the Starlink satellite constellation, which has become an increasingly common source of UAP reports, and 2% were conventional aircraft. This leaves a subset of cases that remain unexplained, not because they represent alien spacecraft, but because there isn't enough data to determine what they are. 21 cases were deemed particularly curious and worthy of continued investigation. 444 reports lacked sufficient data to allow analysis and were placed in an active archive where they might be revisited if additional information becomes available. The report emphasizes several key points. First, to date, AARO has discovered no evidence of extraterrestrial beings, activity, or technology. None of the resolved cases have pointed to advanced capabilities or breakthrough technologies that would suggest something beyond current human engineering. The patterns in UAP reports are consistent with ordinary objects being misidentified under conditions that make identification difficult, such as unusual lighting, atmospheric effects, or unfamiliar viewing angles. Second, the geographic distribution of UAP reports correlates strongly with the locations of U.S. military assets and sensors. Reports cluster around military bases, operational areas, and testing ranges, not because aliens are particularly interested in these locations, but because these are the places where sophisticated sensors are monitoring the sky and where trained observers are present. This is a classic example of observation bias. You find things where you're looking for them. Third, many UAP reports can now be attributed to the rapid expansion of satellite constellations, particularly SpaceX's Starlink system. When these satellites are freshly launched, they form distinctive chains of lights moving across the night sky, a sight that can be quite startling if you're not expecting it. Commercial pilots have reported these as UAPs, only to have the sightings later correlated with Starlink launches from Cape Canaveral. The report also notes 3 cases where military air crews reported being trailed or shadowed by UAPs, but investigators found no evidence linking these incidents to any foreign power. This is an important distinction. Even if something remains unidentified, that doesn't mean it's alien. It could be experimental aircraft, unusual atmospheric phenomena, equipment malfunctions, or optical illusions. The word unidentified simply means we don't know what it is, not that we know it's extraterrestrial. Congressional hearings have featured dramatic testimony from former military personnel and government officials, claiming that the US government possesses alien spacecraft and has been reverse engineering alien technology. One witness, Luis Elizondo, a former Defense Department official, testified that advanced technologies not made by any government are monitoring military installations, and that the US is in possession of UAP. Another witness, a retired Navy Rear Admiral, stated his belief in non-human higher intelligence. But testimony, however dramatic, is not the same as evidence. No physical proof has emerged. No alien craft has been produced. No wreckage has been displayed. No reverse-engineered technology has been demonstrated. AARO's extensive historical review, covering claims dating back to the 1940s, found no verifiable evidence for claims that the US government has access to or has been reverse engineering extraterrestrial technology. The office notes that many UAP claims originate from a consistent group of individuals involved in UAP-related media and advocacy. These claims tend to reference each other in circular fashion, creating an echo chamber where unsupported assertions are repeated until they acquire an aura of legitimacy through sheer repetition. But repetition doesn't create evidence. This doesn't mean that everyone reporting UAPs is mistaken or lying. The human perceptual system, sophisticated as it is, can be fooled. When viewing objects at extreme distances or in unusual conditions, the brain makes assumptions to fill in missing information, and these assumptions can be wrong. A small object close to the observer can appear identical to a large object far away. Motion parallax can make stationary objects appear to move. Atmospheric conditions can create optical illusions. Instrument artifacts can generate false readings. Trained observers are better at avoiding these errors, but they're not immune to. Additionally, there's a cultural dimension to consider. The idea that governments are hiding evidence of alien contact has been a staple of popular culture for decades. This creates expectations, primes people to interpret ambiguous experiences in terms of alien visitation, and generates social rewards for those who claim insider knowledge of government conspiracies. Without dismissing sincere reports, we must recognize that the sociology and psychology of UFO belief are complex phenomena worthy of study in their own right. The scientific position on UAPs is straightforward. Approach each case with an open mind, but demand rigorous evidence. Examine the data carefully. Consider all possible explanations. Test hypotheses against observations. Be willing to say "I don't know" when the evidence is insufficient. Don't jump to extraordinary conclusions without extraordinary evidence. And so far, the evidence for alien spacecraft visiting Earth simply isn't there. The Pentagon's investigations
conducted by qualified personnel with access to sophisticated data, have consistently found mundane explanations or insufficient information, never alien technology. This doesn't prove that such visitations never occur, but it does mean that the dramatic claims require much better evidence than they currently have. The search for extraterrestrial intelligence is a legitimate scientific endeavor, pursued by serious researchers using rigorous methods. UAP investigations, done properly, can contribute to aviation safety and national security, but conflating unidentified observations with alien visitation, jumping from "we don't know what that was" to "it must be aliens," is neither scientifically justified nor helpful. When and if we ever do find solid evidence of extraterrestrial technology, it will be through careful analysis, reproducible observations, and physical evidence that can withstand scrutiny, not through anecdotes and testimony, however compelling they might seem.
The search for extraterrestrial life, whether it's listening for radio signals, analyzing exoplanet atmospheres, or investigating Martian rocks, takes place against the backdrop of some profound theoretical questions. Two frameworks in particular have shaped how scientists think about the likelihood of life beyond Earth: the Drake equation and the Fermi paradox. The Drake equation is not really an equation in the mathematical sense. It's more of a framework for organizing our thinking, a way of breaking down the question how many intelligent civilizations are in our galaxy into manageable parts, formulated by astronomer Frank Drake in 1961 as an agenda for a conference on the search for extraterrestrial intelligence. It lists the factors we'd need to know to estimate the number of civilizations that might be broadcasting signals we could detect. The equation considers the rate at which stars form in our galaxy. What fraction of those stars have planets? How many planets per star are in the habitable zone? What fraction of those habitable planets actually develop life? What fraction of life-bearing worlds develop intelligent life? What fraction of intelligent species develop technology capable of interstellar communication? And finally, how long such civilizations typically broadcast before they're gone, whether through destruction, evolution beyond the need for radio, or simply choosing to remain silent. If you assign optimistic values to each term, you can calculate that our galaxy should contain thousands or even millions of technological civilizations. If you're pessimistic, particularly about the likelihood of intelligence arising, or about how long civilizations typically survive after developing technology, you might conclude we're the only one, or at least the only one currently broadcasting. The equation reveals how much we don't know. Several of its terms are complete mysteries. How common is the transition from non-living chemistry to living biology? We have exactly one example: Earth. Did life arise easily here, or did it require an improbable series of events? We can't yet answer that. If life does arise, how likely is it to become complex, multicellular, and eventually intelligent? Again, we don't know. And perhaps most crucially, how long do technological civilizations typically last? This last question is particularly unsettling. Humans have had radio technology for little more than a century. We've had nuclear weapons for 8 decades. We've been altering our planet's climate for several decades. These are not unrelated facts. The same scientific and technological capabilities that allow us to broadcast signals into space also give us the power to devastate our biosphere, whether through nuclear war, environmental catastrophe, or technologies we haven't yet invented. This brings us to the Fermi paradox, named after physicist Enrico Fermi,
During a 1950 lunch conversation about extraterrestrials and interstellar travel, Fermi famously asked, "Where is everybody?" His point was simple but profound. If technological civilizations are common, and if they're older than ours, having had millions or billions of years to develop, why haven't they colonized the galaxy? Why haven't we encountered them? Space is vast, certainly, but it's not that vast on cosmic timescale. Even traveling at speeds far below the speed of light, speeds we can imagine achieving with foreseeable technology, a civilization could spread through the galaxy in just a few tens of millions of years. That sounds like a long time, but it's brief compared to the multi-billion-year age of the galaxy. If intelligence commonly arises, and if intelligent species have a tendency to explore and expand, a tendency that seems almost universal among Earth life, then the galaxy should be full of evidence of alien civilizations. Yet we see nothing. The contrast between the apparently high probability of life suggested by the Drake equation and the observed absence of any sign of it creates the paradox. Many solutions have been proposed over the decades. Perhaps interstellar travel is impossible or impractical, despite our assumption. Perhaps civilizations stay home, content with virtual realities or transcendent experiences that make spreading through physical space uninteresting. Perhaps they're here but hiding, deliberately avoiding contact for reasons we can't fathom. Perhaps we're living in a cosmic zoo or nature preserve, observed but not interfered with. More ominously, perhaps there's a great filter, an evolutionary hurdle so difficult that almost no species manages to overcome it. The filter could lie behind us, meaning the emergence of intelligence is incredibly rare and we're extraordinarily lucky to exist. Or it could lie ahead, a challenge that destroys civilizations shortly after they become technological. Perhaps most species invent nuclear weapons or artificial superintelligence or climate destabilizing technologies and don't survive the consequences. If the filter is ahead of us, then the silence of the cosmos becomes a warning. It suggests that the fate of technological civilizations is typically extinction, not expansion. Another possibility is simple. Perhaps we're among the first. The universe is about 13.8 billion years old, but the early universe was inhospitable to life. The heavy elements necessary for rocky planets and carbon-based life had to be manufactured in the cores of stars and distributed through supernovae explosions. This took time. The first Earth-like planets couldn't have formed until several billion years after the Big Bang. If life typically takes several billion years to evolve from single cells to intelligence, then perhaps technological civilizations are only now beginning to appear throughout the cosmos. We might be early, among the first species in the galaxy to ask, "Where is everybody?" Or perhaps life is common but intelligence is rare. Intelligence, as marvelous as it is, isn't necessarily a survival advantage in most environments. The vast majority of species on Earth aren't intelligent by any reasonable definition, yet they survive perfectly well. Intelligence is energetically expensive, requiring large brains that consume substantial resources. It only pays off in specific ecological niche. If intelligence is a rare evolutionary path, much rarer than we assume, then planets might be teeming with microbial life, perhaps even multicellular life, but very few worlds ever develop creatures capable of building radio telescopes. Or maybe we're simply looking wrong. Perhaps advanced civilizations use communication technologies we haven't invented and can't detect. Perhaps they communicate through methods that leave no trace we'd recognize. Perhaps they've moved beyond electromagnetic radiation entirely, using quantum entanglement, or dimensional manipulation, or concepts we can't even imagine.
We're listening for radio signals and looking for optical lasers, because that's what we know how to detect. But the universe might be full of communication we're blind to. Every one of these explanations has defenders, and none can currently be ruled out. The data simply aren't sufficient to distinguish among them. This is frustrating but also exciting. It means the answer remains unknown, waiting to be discovered. It means the searches continue to matter, continue to hold the possibility of revolutionary discovery. What's clear is that the Drake equation and Fermi paradox aren't just abstract puzzles. They frame the search for life beyond Earth, helping us understand what we're looking for and why we might not have found it yet. They remind us that the question of whether we're alone is not just about biology or astronomy, but about philosophy, about understanding our place in the universe, about grappling with what it means to be an intelligent species in a cosmos that seems, at least from our current vantage point, remarkably quiet.
Given the lack of confirmed detections, the absence of definitive proof, and the enormous uncertainty involved, why do scientists continue to take the search for extraterrestrial life seriously? Why do institutions invest resources? Why do researchers dedicate careers? Why does the scientific community treat this as legitimate inquiry, rather than fringe speculation? The answer begins with the fundamental nature of science itself. Science is not just about confirming what we already believe. It's about asking questions, testing hypotheses, following evidence wherever it leads. The question of whether life exists beyond Earth is one of the most profound questions we can ask. It touches on biology, chemistry, astronomy, geology, and philosophy. It asks about the nature of life, the conditions necessary for its emergence, the likelihood of intelligence, the fate of civilizations. These are questions worth pursuing, even if the answer turns out to be that we're alone. Moreover, the tools and methods developed for astrobiology have value far beyond the search for aliens. When scientists study extremophiles, organisms that thrive in Earth's harshest environments, they learn about the limits of biology and discover new biochemistries with potential applications in medicine and industry. When engineers design instruments to detect biosignatures on Mars, those same technologies often find uses in environmental monitoring, medical diagnostics, or other fields. The search drives innovation. The scientific approach to finding life elsewhere is notably different from popular culture's treatment of the topic. Scientists don't assume we'll find aliens under every rock or behind every unexplained observation. They apply rigorous standards of evidence. They consider alternative explanations. They design experiments to test hypotheses. They welcome criticism and peer review. They're willing to wait for better data rather than jumping to conclusions. This is why the alloning around potential biosignatures is so carefully qualified. When researchers say they've found a potential biosignature or possible evidence of life, they're not hedging or being deliberately vague. They're being precise. They're distinguishing between what the data actually shows and what they might hope it shows. They're acknowledging uncertainty and inviting further investigation. The scientific community has developed specific frameworks for evaluating claims about life beyond Earth. The confidence of life detection scale, the COLD scale, provides a graduated ladder of increasing certainty. Early rungs involve detecting conditions consistent with life: liquid water, organic molecules, energy sources. Middle rungs involve finding patterns or substances more readily explained by biology than by chemistry alone. Upper rungs require detecting molecular complexity, spatial organization, or functional systems that strongly suggest biology. The highest rung would be detecting something unmistakably alive, perhaps capturing an image of a cell dividing or observing metabolism in action. Similar frameworks exist for evaluating potential technosignatures, signs of technology. A single unexplained signal won't suffice. Scientists need the signal to repeat, to come from a specific location, to have properties that would be difficult to explain through natural process. They need to rule out terrestrial interference, instrument artifacts, and astronomical phenomena that might mimic an artificial transmission. Multiple independent detections using different instruments would strengthen the case. Analysis by multiple research groups would add confidence. Only after passing through these filters would a detection be considered potentially genuine. This demanding standard exists for good reason. The claim that we've found life beyond Earth would be one of the most significant scientific announcements in history. It would revolutionize biology, astrobiology, and our philosophical understanding of our place in the universe. Getting it wrong would damage the credibility of entire fields. False alarms, however well-intentioned, create skepticism and undermine legitimate research. Better to be cautious, to demand extraordinary evidence for extraordinary claims, than to declare victory prematurely. Importantly, negative results also matter in science. If we search thoroughly for life on Mars and find nothing, that's a result. It tells us something about how common or rare the origin of life might be. If SETI searches thousands of star systems and detects no signals, that constrains how common technological civilizations are in our galaxy. Null results help us understand the universe even if they don't provide the dramatic discoveries we might hope for. The search also continues because the technology keeps improving. The telescopes we're building now are far more powerful than those of a decade ago. The instruments we're sending to Mars and planning for Europa are more sophisticated. The computational tools for analyzing data are more capable. Machine learning algorithms can find patterns that human analysts would miss. Each technological advance opens new possibilities, allows us to search deeper, broader, more sensitively than before. And there's something else, something harder to quantify but no less real. The search for life beyond Earth inspires people. It captures imagination in a way few scientific endeavors do. Young people become interested in science because they want to search for aliens, and along the way they learn physics, chemistry, biology, engineering, mathematics. The public supports space missions because they want to know if we're alone. Politicians fund astrobiology research because their constituents care about the answer. This inspiration, this public engagement, has value. It makes people more scientifically literate, more appreciative of the scientific method, more willing to support research even when immediate practical applications aren't obvious. Scientists take the search for extraterrestrial life seriously because it's scientifically justified, methodologically sound, and philosophically profound. They don't claim to know the answer. They don't promise success. They simply acknowledge that the question is worth asking, and that we now have tools sophisticated enough to begin answering it. Whether we're alone or not, the search itself teaches us about life, about planets, about the universe, and that ultimately is what science is for. Not just finding answers but learning to ask better questions. We know that planets are common, that habitable worlds likely number in the billions, just in our galaxy alone. We know that the building blocks of life, organic molecules and liquid water, exists throughout the cosmos. We found tantalizing hints on Mars, intriguing chemical signatures on distant exoplanets,
conditions that could support life in the oceans of icy moons. But we haven't found life itself, not yet. The evidence remains circumstantial, suggestive, but not conclusive. Every exciting discovery comes with caveats, with alternative explanations, with the need for more data. This is exactly as it should be. Science doesn't rush to judgment. It waits for evidence to accumulate, for hypotheses to be tested, for multiple lines of inquiry to converge. The search continues, more sophisticated and far-reaching than ever before. Every year brings new exoplanet discoveries, new missions to our solar system's most promising worlds, new technologies for detecting the subtle signs of life. Within the lifetimes of people alive today, we might finally answer the ancient question that has haunted human consciousness since we first looked up at the stars and wondered, are we alone? Or we might not. The universe might be silent, sterile, empty of life, except for our small blue planet. Even that would be an answer, a profound one. It would make life on Earth infinitely precious, a cosmic rarity to be cherished and protected. Either way, the search itself ennobles us. It represents humanity at its best, curious, persistent, willing to ask difficult questions and follow the evidence even when it leads to uncertainty. It demonstrates our desire to understand, to connect, to find meaning in the vast darkness. Before you drift off to sleep, if you found this journey through the cosmos interesting, if you'd like to explore more questions at the boundary of human knowledge, please consider liking this video and subscribing to Science Lullaby. Your support helps us continue creating content that educates while helping you relax. Thank you for listening, and sweet dreams as you contemplate the possibility that somewhere out there, under alien stars, other minds might be looking up into their sky, asking the same questions we are, wondering if they too are alone.